For the types of databases that we're going to be using, we're going to be using the Java API for connecting to SQL databases, right? So this is a standard Java package that you can use, right? Don't expect you to know how to use it yet, don't worry about that. That's something that we'll focus on next semester, right? But for those of you who want to look ahead, you can look at that. And we're going to use a particular form of SQL, which is an open source one that anyone can access and download and install on pretty well any platform called MySQL. So it has all the functionality of a full-blown, well, maybe not all the functionality, but all the core functionality of a full-blown SQL database. So in terms of what I'm going to talk about today, first of all, I'm going to start with mathematical relations. And the relationship between those mathematical relations known as relational algebra and SQL. We'll talk about how to define and manipulate data, the more complex queries you can do well, first of all, straight off queries, how to get information from a database, but then aggregate functions that can manipulate the data in different ways and do quite complex query extraction from your database. I'll briefly talk about optimizing and indexing queries, and also briefly about the API and MySQL. As I say, those ones won't be incredibly relevant until you use them in practice next semester, right? So if you want to do some additional reading, these are the chapters from those two textbooks, same books that I referenced last week, different chapters. Okay, so we're going to start with relational algebra. Relational algebra goes back to the early 70s. And it's basically the idea that we have, with data stored in tables, we want ways of combining it and accessing different things, that sort of thing, right? So we have, first of all, set operations, so union, intersection, difference. So the union of two sets is basically both put together. The intersection of two sets are those bits which are the same in both of them, and the difference are those bits which are not the same in them. Product of, when we're talking about sets, is basically combining the two to create a larger item. So if you think of it in terms of tables, if you've got two tables of 2 and 3 columns each, it's creating a new one of 5 columns, right? Select, this is where we start getting information from our databases. So finding the tuples. Now a tuple, who knows what a tuple is? Nope, that's fine. Okay, so a tuple is in itself a set of elements, right? So it is any number. It could be 2. You can have an empty tuple, in fact. You could have just 1 item, 2 items, 3 items, whatever. But all tuples that are the result of a query should be the same size, right? And so what it means is that you're selecting particular columns from a database usually. So you might have a database that has 10 columns in it, but the tuples that are returned might have only 3 because you're only selecting 3 of those columns from the database. And each tuple represents a row out of those things that you've selected, right? So you can think of them as kind of rows in another database if you want. Right? Okay. Predicate is another technical term. It basically means a condition. Okay? So this is, we're selecting things from a table according to a certain condition. So we might select all students who have a grade of greater than 40. and the grade greater than 40 is your predicate. Right? When we project onto a set of data, what we're doing is we're removing duplicates from it. Okay, so here it says create a shorter relation with fewer places. It basically means if you have two items in your table that have the same values in the entire row, it reduces it down to a single instance of that row. That's what projection does. Join is similar to product. It's a way of combining tables, but usually what happens is that you merge one or more places. So for example, if you've got two tables that have two columns which are the same, and you're combining them, so the first one has two columns, one of which is a key, and the second one has three columns, another one being the same key as in the first one, right? So we have 5 columns in total, and if we did a product, we would have 5 columns in our resulting table. If we did a join, we would only have 4 columns, because those 2 columns, the one in each table that's the same, would get combined into one in the final. Okay? So that's the difference between a product and a join. Okay, so that's relational algebra. We also have relational query languages, and they are languages, if you like, another type of programming languages, which are designed for describing queries into a relational database. And the most common one that you'll ever come across is SQL, which comes in lots of different forms, but the same basic types of presentation of the queries works for all of those different forms. You might need very slight tweaks when you move between one and the other, but essentially, if you learn to write queries for MySQL, you'll be able to write queries for Oracle. Okay? Some of the queries that you might write for Oracle won't be able to write in MySQL because it's a more simplified form of SQL, right? But there will be ways of doing the same thing, you just have to might write something more complicated in order to achieve the same thing. Oracle gives you shortcuts to do certain sorts of things, right? So, structured query languages, the key thing about them is that they're declarative. Okay, now what does declarative mean? Well, most of your programming that you do is going to essentially be procedural. Right? You're telling the computer what to do step by step. Right? There are declarative programming languages other than query languages, but you're unlikely to encounter them. They're very specialized. Right? What a declarative programming language means, though, is that you are stating what is required, not how to get it. Okay, so you're not stating the procedure for getting the data from the database, you are stating the conditions to be met in order to extract data from the database. Okay? And I think as you start to develop your own queries, you will understand that it's actually quite a good way for accessing information. Okay? We think about information, filtering and manipulating and that type of thing in our own heads in a declarative way. Right? Relational algebra is the glue that takes this structured query language and turns it into something procedural that the computer uses to actually get the data from the database. Because computers are procedural, right? Everything has to be done in terms of this step followed by that step followed by that step. I mean, that's what computer byte level code is. It's a set of procedural instructions. So even if we can write very nicely at an abstract level, a declarative programming language, at some point it needs to get turned into something procedural. And that's what the relational algebra does for structured query languages. So that's why the first half of this lecture is about the relational algebra. Okay, so what's an algebra? You will have used algebra in maths, in terms of mathematical equations, that sort of thing, where you have variables and you might be plotting graphs or something like that. So you've all done some form of algebra or another. Even if it was back when you were in early years of high school, you will have done some algebra, right? But relational algebra is a special type of algebra, and you probably haven't encountered it before. But in general, with algebra, operators map values taken from the domain into other domain values. So you have functions that map x into something else, right? And so you end up, saying f of x equals x squared, and you get a nice curve on your graph, that type of thing. So you're taking one input and producing another output. It's the basic idea of an algebra. So an expression involving operators and arguments produces a value in the domain. It's starting to sound like you're turning it into a computer program, and that's quite deliberate. But that's essentially what you're doing when you're applying a mathematical function as well. Okay, so when the domain is a set of all relations, and the operators with those relations, we get the relational algebra. And we refer to an expression as a query, and the value that's produced as the query result. So we're talking about the relation between the input and the data that we get out. So the domain is a set of relations. The basic operators are those things that I was talking about earlier. So first of all, the most obvious one is select. We want to select things from our database. We want to project tables in our database to create new tables. We want union of tables. I talked about the difference between project and union before. We might be interested in the set difference or the Cartesian product. We have also derived operators, which are the set, intersection, division, which I may or may not discuss today. It's perhaps more complicated than is needed, and join. Okay? Now, it's procedural because the relational expression specifies the query by describing an algorithm, the sequence in which the operators are applied for determining the result of an expression. Okay, so the algebra itself doesn't say, look at the table row by row, select the things that are, but underlying that select operator, there will be something which tells the computer exactly how to do it step by step. Right. So conceptually, because some people like visual representations better, we start off with our query in SQL. It goes through a parser, which turns it into a relational expression. Right? That expression then gets optimized so that the search is faster, basically, and which in turn generates code, which goes and grabs it from the database. Okay? It's the same way that any compiler works, really. Right? It takes a high-level language, goes through a series of steps to turn it into computer code. And it doesn't matter what form that high-level language is in, whether it's already a procedural language, like Java essentially is, right? Or if it's a functional language, or a declarative language, or whatever type of language it is, eventually it has to turn into something procedural, and the compiler is the thing that goes through that process. Okay, so as I said, if you're dealing with databases, key thing, well, apart from storing data, the key thing you're going to be doing is looking it up. And so we need a select operator. Okay, the select, so in relational algebra, this sigma is the symbol that represents the select operator. It takes a condition and the relation that we're looking at. So condition is going to be the thing that we want those things to be selected, where that condition is true. Right? So for example, if we've got this table person, and I say select where hobby is equal to stamps from person, I will get those rows which match hobby equal to stamps. Okay? For the condition itself, the most simple thing is all the standard operators. So comparative operators, less than, greater than or less, greater than or equal to, not equal to. Right? And you can set selected equal to a constant or selected equal to an attribute. An attribute is basically just a variable that you assign a value to. You can also use ands, ors, and nots. Okay, so you can select against multiple conditions if you want to. So, for example, further examples. We select where the identifier has a value of greater than 3,000 or the hobby is equal to hiking from that table person that we had before. We select all the people between 3,000 and 3,999. We select all the people who don't have the hobby equal to hiking. And that's exactly the same. Okay. Remember, we're talking about relational algebra, not something that needs to be put into a computer language, so whichever form you like for not equal is appropriate. Okay, if you're doing it on a computer, you don't have access to that symbol, but this is a handwritten thing. Quite typed. You get the idea. Okay, so select is the most basic of operators that you need. Project is a useful one as well. Okay, so here, what we're doing is we're removing duplicates. We want to get, sorry, we're not removing duplicates, we're just selecting the columns that we are interested in. All columns that we're interested in. Right? Now you could do that in other ways. And if you're doing it in SQL, there are multiple ways of doing it. But in relational algebra, you'll typically do this way. So what we're doing is we're taking the person table and we're saying, I want the names and hobbies from it. Creating a new table that just has those two columns to it. Okay, that's particularly useful if you've got a table that's got lots and lots and lots of columns in it, so you haven't bothered to get it into a normalized form, and you're only interested in the data from a small number of those columns. Okay? You can create your own table in that case, which contains just the information that you're interested in, and then you can do all your searching on just that information. It means that you're going to be working with a lot less memory. You know, if you've got a table with 20 columns in it and you're only interested in 3 of them, getting rid of those other 17 columns will save you a lot of memory space, especially if you've got lots of items in your table. Here's an instance where the resulting table has 1 fewer rows in it. Okay, so the difference between the two of them is that when I was looking at the name and the hobby, every row from this table, which referenced name and hobby, was unique. Right? So that's why I get the same number in both tables. In this case, I'm looking at name and address. John has 2 hobbies, right? But I'm not referencing hobby in this table, so I don't need to have John twice in it. Okay? John has 1 name and address, so I can eliminate one of those rows from the table. Well, not I can, but the project operator does automatically eliminate that table, that row. Okay, so a relation is a set of tuples. Each row in the table is a tuple. And so we're talking about sets of tuples. Set operations should apply. If we combine 2 relations with a set operator, all its elements have to have the same structure. Okay, now that, if you think of it in terms of tables, of course that's the case. If your result is a table, you're going to have a table with the same number of columns in it, and every item in the table is going to have that same number of columns. There might be instances where they have null values in them, but they still have to exist, right? Okay, so the consequence of it is that we're limited to union-compatible relations. But don't worry too much about what technically that means. So one of these relations is what's known as a product. So if I have, say, 2 tables here, cities and quantities, and I take the product of those 2 tables, what I end up with is one large table that has 3 columns corresponding to the 3 columns in the original tables, and 4 rows, because it needs to combine every possible. So London with each row here, and Paris with each row here. Okay. When you combine tables like this, it always creates a compound primary key. So each of these tables had a single primary key. Okay. The resulting table has both of those primary keys as its primary key. Okay, for these particular tables, there's no other real sensible way of joining them because we don't have any relationships between the data in that table and the data in that table. Okay, there's nothing tying the two of them together. Nothing common between the two tables. A more common circumstance is where you do have shared information in the two tables. Right? So in this case, we have what's known as a natural join. And what we're doing is we're looking at cases where you have a match between the two of them. Right? So a natural join you have to specify what you're going to join on. Okay? Sometimes they'll have the same name, as in this case, so there's product ID in both things, so that's the obvious thing to join on. But sometimes they'll have the thing that's shared between them will have different names in different tables within the database, but still you know that they're the same thing, right? So it's possible to do it that way. Okay, so here we've got one table with all the orders, so the different cities, they're ordering different products. In the other table we have, well, it's quantities, it's, I assume an inventory database or something. So we've got 1,000 of product 1 in stock, 100 of product 1, 200 of product 2, 100 of product 3. And we don't have product 4 mentioned at all, despite the fact that it's been mentioned in the other table. Presumably it's out of stock or something, right? Or a discontinued item, or, you know, for whatever reason it's not in that table. The natural join will create a combined thing. So this, rather than having 4 columns that were in the 2 separate tables, what it's doing is it's sharing this product ID between the 2 of them, right? And it's ignoring the ones where it doesn't match between the 2 tables. So they just get thrown away effectively. Okay, so London product 1, there's a quantity of 100. London product 2, there's a quantity of 200. And Paris product 2, there's a quantity of 200. There's nothing for Paris product 4, and there's nothing for product 3. Okay? It's not the only type of join that you can do, though. Okay, so the natural join is where we're joining on the same named items, right? Product ideas in the case of the other. Now remember, I also said you can join on explicitly named columns where you know that they have the same thing, but actually they've been labelled differently in different tables or something like that. So that's what's known as an inner join. Then we have these outer join cases. So remember, in that previous example, we threw away, what was it? Paris product 4 and from the first table, and product 3, 100 from the second table, right? What have I done? Okay. The outer joins are basically ways of preserving those things. A left outer join will include the ones from the first table that have no match in the second. A right outer join will include the ones from the second table that have no match in the first. And a full outer join will include both of them. And the way that it includes the items that have no match in the other is it simply puts null where there was no match. Right? So, looking at an example of a left outer join, this one here in the first table has no match in the second table, so we still include it in the join, but we've got nulls there. Okay. The right outer join and the full outer join, similar sort of process. Okay, notice here that rather than merging the product ID thing, I have two separate ones. Right? The reason that happens is to make it quite explicit that the item is missing here. Right? And it uses a reference based upon the table name to specify which product ID we're talking about in each column. Okay, so that's the algebra, right? There is a lot more to algebra, but I don't want to go into the details of it because I don't think you need to know it at that level of detail. I wanted to explain to you the basic principles of the algebra so that you know what's going on behind the SQL, right? And just know that there is a lot more to it than this. And if you want to learn more, those textbooks will cover it for you. Okay. More important though, and this is something that you really do need to learn, not completely today, okay, you're getting an introduction to it today, you will learn it in considerably more detail next semester when you're doing your group project. Okay, so SQL is the standard database query language. Back when I studied databases, there were a few alternatives around. SQL was still the dominant one, but it wasn't absolutely dominant the way it is in today's world. Okay. SQL stands for Structured Query Language, and back in 1987, they decided that it isn't even an acronym anymore, it's just SQL. Some people will call it SQL. Okay, you will hear people call it SQL. And it continues to evolve like most programming languages, so we get more and more types supported in it and that sort of thing. Right? But if you look at Java now compared to what Java was in the 90s, it's a very different thing as well. Okay, in fact, yesterday I saw that they have just released the draft version for the new release for the C programming language. And C has been around since the 60s, right? So it is based on relational algebra and relational calculus. It provides a syntax for defining, manipulating, and querying tables. So you need to be able to create tables, to change tables, to add data to tables, and to query tables. Okay? The queries return lists, not sets. And Cod, the person who defined relational algebra, really hates this. It says databases should be all set relations, not list relations, right? But you do get lists. And what does that mean? You can get duplicates. Okay, so sets, every item in a set is unique, right? Lists, not necessarily. Okay. And it doesn't match properly with relational algebra either. For example, select in SQL does a relational algebra project. Right? So it will select the columns. In order to actually do a select in SQL, you have to use a where clause to put the condition onto it. So select on its own doesn't have conditions associated with it. You have to add a where clause in order to do conditions. Okay, so the first thing we need to do if we're using databases is to actually create the tables. You can't have a database if you don't have a table to put your data into. So here's an example where we're defining a table and we're identifying primary and foreign keys within that table. We're creating a table called book title. Huh? The first item in this table is the ISBN, which is an integer, 13 places. So this is, we're assuming ISBN 13, or maybe we'll be able to use ISBN 10 because it will still fit within the 13. Yeah. So, but it's a field width of 13, and it can't be null. So it's not null, and it's a primary key. Okay, you certainly want your primary keys to be not null. We have a name, up to 30 characters, and an author, up to 20 characters. Okay. Key point here. The difference between char and varchar is the padding. Right? So basically what it's saying is that if we define something to be a fixed number of chars, then, and it only uses 5 of the 10, for example, the remaining 5 characters will get padded with nulls or zeros. Right? Whereas if it's varchar, it doesn't get padded. So it's about space usage. Okay, second table we're creating is called book copy. The key here is the Dewey ID, which is, again, not null. We've got on loan type boolean with a default value of false. So when people insert data into the table, it's assumed that it's not on loan. Kind of makes sense. When a book's new in the library, it hasn't been loaned out yet. We have the ISBN, as we had in the previous table. And then separately, we are saying that this is a foreign key referencing the table book title. Okay, so we're making the link between the tables explicit.
Excuse me.
Yep.
I have a question. Why they use the constant not null with the primary key? Because primary key it's unique and not null.
Because SQL is painful and you need to say that the primary key is not null. Yeah.
If I try to insert a value or not to insert value and primary key, it will accept non-value.
If you don't specify that, yeah, if you haven't specified your primary key is not null, it will happen that it will accept it with a null item in that field.
This is must with
So
primary
that would, yeah, you must have not null with your primary key. Okay, you're right. It would make sense to just by default force it to be not null, and I don't know why it doesn't. Some designers. There probably is a logical reason for it somewhere, but I don't know what it is. To me, it would be just so much easier to force any primary key to be not null. Okay, remember last week when we talked about linker tables as well? Right? So we did actually look at the case of the loan as a linker table. So we would need to create these linker tables at the same time that we're setting up our database. So we need to identify compound primary and foreign keys here. Right? So we have the loan table, in this case the primary key is identified after all of the other things. Okay, because we're doing a compound primary key, so we need to know what the other things are. Right. So we've got the member ID, the copy ID, the issue date, the due date, and the primary key is the compound thing made up of the member ID and the copy ID, because there can only be one mapping there, so it has to be unique. And then we have the foreign key referencing each of the other two tables. Oh, okay. So the first foreign key, member ID, your column is the same in both tables. Okay, so you don't need to be explicit about what it is in borrower. If you're not explicit, it assumes that it's the same. In the second foreign key here, copy ID in this table is linked with Dewey ID in the book table. The book copy table, sorry. Right? So these two are assumed to be the same thing, despite having different names in the different tables. Okay, so those three tables that we've just created are enough to record all the patrons of the library, record all the books that you've got in the library, and record all the loans that you're managing in the library. Because the tables alone aren't much use without data in them. Right, so obvious things that we want to do is populate the tables. So here we're inserting into book title these values. It's not a very good library, we've only got 3 books. Right? So, but you could put as many things as you wanted in there. They're just essentially comma-separated lists of rows. It would be easy to take a text file or a comma-separated variables file and feed it into that query. Right. Most languages will go one step further than that, and you don't even have to write the parser for it. They will just take the comma-separated variable file as input, and you can insert it into the table. Right? So populating the tables is a relatively straightforward thing. So of course I have to provide the functionality for it. When you're doing the initial population of the table, obviously you're going to have large amount of data going in. But on a day-to-day basis in the library, they might be adding a few books at a time, and so the librarians want to be able to do it manually in this sort of format. Okay, here's an example where we want to change the status of a thing. So here it looks like this book has just been returned. So we're doing an update to set the loan to false, where the Dewey ID has this value, representing the specific book in the system. And at the same time, we want to delete that reference from the linker table because it is no longer on loan. Okay, so we've changed the book copy table to set its loan thing to false, and we've deleted it from the loan because there's no longer a link between that borrower and the book. Okay, simple query. In SQL, it's select, which is different to the relational algebra select, just to be confusing, right? But essentially what we're doing in SQL is saying we select the columns where some condition is true. In relational algebra, it would be project columns where we're selecting the predicate. Okay, so the expression in relational algebra is more complicated than it is in SQL. Right, here we're selecting the name and author from the book title table where the ISBN has a particular value. So we're finding out what the name and author is for that particular ISBN. Here's a more complicated one where we're getting the name and the author where the name is like Harry Potter percent. Percent is a wild card. Okay, so it's any book title that starts with Harry Potter. Why starts with? Because of the percent sign. Why? So it wouldn't match who is Harry Potter. Why not? If the book title was Who is Harry Potter?
Does it start with Harry Potter?
Yeah, so if I wanted it to match Harry Potter anywhere in the title, I would have to have a percent before it as well. Okay? So the percent represents the bit that can be anything. Here it starts with Harry Potter, followed by anything. Okay, here, another selection where I'm getting the name is in this set. So it's getting all the books called Twilight and the books called New Moon. And I've also specified that the output should be ordered by the author first and then the name. Okay, so remember the output is a list. This is going to be a list sorted by author. And where there's two by the same author, it will be sorted by the name of the book. Okay, so this again, this is just the tip of the iceberg when it comes to the select operators in SQL. You can do very complex things with your where clauses, which produces some very sophisticated manipulation of the tables that you've got. Right? Sometimes it's easier to do simple queries and then use the results of your queries to perform more queries and that sort of thing. Sometimes, if you become an expert at SQL, it's better to roll it in here. The reason that it tends to be better to do everything you can in a single query is because then the compiler can optimize your query for you. If you have a series of queries where you're taking the output of one and then performing more manipulation on the output of that and so on, you're reducing the opportunity for the compiler to optimize for you.